Hi everyone, today another video in the electrochemistry series looking at predicting the direction of reactions and feasibility. So in the previous video we looked at the electrochemical series and looking at electrode potentials, standard electrode potentials, and we saw how we could calculate the overall cell potential using these potentials for the half cells. And remember that we measure these half cell values by connecting up our half cell to the standard hydrogen electrode. We can't actually measure the half cell on its own. It's impossible to do that. But we can also use the standard electrode potentials to decide on the feasibility of a redox reaction. Now, a redox reaction is just an electron transfer reaction, essentially an electrochemical reaction in this sense. And the feasibility is just talking to us about whether a reaction will actually occur in the given direction. It's very similar to the idea of feasibility and spontaneous reactions in thermodynamics and Gibbs free energies, for example. There, if we have a spontaneous reaction, the reaction goes without us needing to kind of do anything, without us needing to put any energy in. And the same thing applies here. If we have a feasible electrochemical reaction, well, this reaction will spontaneously happen. And this is because, remember, that electrons will always flow from negative to positive. They're repelled from a negative region, attracted to a positive region. They never move in the opposite direction. That would be the non-spontaneous direction. The spontaneous or the feasible direction is to go from negative to positive. So in order to see which direction is feasible and to essentially work out the feasibility of a reaction, the first thing we need to do is we need to go to our electrochemical series and we need to write out the half equations of interest and their E-cell values. We're then going to draw out the electrical cell, similar to how it is depicted on the right in that pictorial representation. And we saw how we could essentially draw this picture from the E-cell values in the previous video. Now the key thing is that when we draw out our diagrams, we need to make sure we label every part of it. So we need to make sure we label what the solutions are, label what the electrodes are, label what the wires are, label what the salt bridge is, label where the voltmeter is, label the electron flow direction, and label the standard conditions. And so we can sort of see this here on the picture on the right. We've labelled our solutions, we've labelled what our electrode materials are, we've labelled the salt bridge, we've labelled our voltmeter. But they haven't written the standard conditions down, but I would always write down that they are 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cube solutions. And just one thing to note, our electron flow flows from negative to positive. But conventional current, what we define as conventional current, remember that current essentially is just the flow of electrons. But what's actually defined as conventional current is from positive to negative. And the reason for this is just because when they defined conventional current, they didn't realise that it was electrons that caused it, and so they just defined it to go from positive to negative. We now understand that obviously it's electrons that are responsible for current, and electrons flow from negative to positive. So it's just a distinction to make sure that you're familiar with. The electrons always flow from negative to positive, but if you see conventional current being talked about, that is told of being flown from the positive to the negative. So we need to work out which electrode is on the left, which electrode is our anode, and which electrode is on the right, which one is our cathode. And we do this by comparing the E-cell values. We saw this again in the previous video of this series. The more negative E-cell value is the one that is more likely to be oxidized, the one that is more likely to lose the electrons, the better reducing agent. And so therefore that one goes on the left, that is our anode. The one with the more positive E-cell value is more likely to be reduced, and that goes on the right, that's our cathode. We then combine our equations by cancelling out the electrons, and then we can calculate, as we saw in the last video, a standard cell potential by doing the right minus the left of those E-cell values. And as we talked about in the previous video as well, if a system contains metal ions but no actual physical solid metal, for example an Fe3 plus Fe2 plus half cell, then we need to use a platinum electrode in that solution because we need to have a solid electrode. And so we have to use platinum, a very sort of inert and reactive but conducting metal. This is also important for half cells where we are using gases. So for example, the standard hydrogen electrode, we have H2 gas. We obviously can't clip a crocodile clip onto a gas. So again, we need an actual solid electrode and we use platinum again. We also talked in the last video about our standard cell representations. And so if we wanted to write this cell representation out for a standard hydrogen electrode connected to the Fe3 plus Fe2 plus cell, well, then the way we would do it is remember that we always have whatever is on the left, whatever has been oxidized is on the left, whatever is on the right on the picture, whatever has been reduced on the right. We follow our electron flow from left to right like it goes from negative to positive in the picture, or we can think of it as our highest oxidation species go next to the salt bridge. So we have our platinum electrode, then we have a phase boundary, phase change into hydrogen gas, then a phase change into the hydrogen ions that are in aqueous solution. That's our highest oxidation species. So it goes next to the salt bridge, 2 vertical lines. We then have our highest oxidation species in the iron half cell, so Fe3 plus. Remember that if it's not a phase change, so in this case both ion species are aqueous, that we use a comma, not a vertical line. So Fe3 plus, comma, Fe2 plus, and then again we need that platinum solid support because we don't have actually any metal in there, any solid metal. And so we have a phase boundary and then solid platinum. And so by writing the more negative electrode on the left, our equation for the E cell value becomes the right minus the left. Now, a little caveat to note as well is that our E cell values tell us about the feasibility, basically the thermodynamics of a reaction. They tell you nothing about the kinetics. It's the same way when you look at enthalpy changes and Gibbs free energies and entropy and all that kind of thermodynamics, that it tells you nothing about the kinetics, nothing about how quickly a reaction can occur. Likewise, kinetics tells you nothing about thermodynamics. That can tell you how quickly something occurs, but not anything to do with how stable the products are or the energy changes. And so like for the kind of thermodynamics we've seen before, where we have the diamond and graphite transition, that graphite is the more thermodynamically stable form of carbon, that all of your nice diamond rings and stuff don't turn into graphite in front of you, because that reaction is so slow, the kinetics are so slow. A similar thing happens in electrochemistry. So it could be that a feasible reaction may not be seen to occur at room temperature because the kinetics are so slow. And so if we have a couple of reactions that could occur, one that is less feasible actually occurs because it is quicker. Now to actually have a look at an example of doing this kind of question. So this kind of question is really common in the exams. It will give you an electrical cell, it will give you an equation, and it will ask you to tell them whether the reaction is feasible. Essentially what it means is the reaction, as they've written it in the question, going to happen? Is that the reaction that actually happens? And so we have this reaction here, silver plus aluminium ions going to silver ions and aluminium. And we're asked, is that feasible? So the first thing to do is draw our picture. So we look at our electrochemical series. We have our aluminium half equation, Al3 plus, there's 3 electrons going to solid aluminium. Remember that all of these in the electrochemical series are written as reductions, gaining the electrons. This gives us our E value, our potential value as negative 1.66 volts. We have our silver half equation. That gives us our potential of plus 0.79 volts. And as always with any electrochemistry question, I've always written the mnemonics. Oil rig, oxidation is loss of electrons, reduction is gain of electrons, and red cat, anox. Reduction happens at the cathode, oxidation happens at the anode. So we can see that our aluminium has the more negative E cell value for that half cell. So that is the one that is the better reducing agent, the more likely to be oxidized, the one that is going to release the electrons. And therefore, if it is being oxidized, it happens at the anode, and our anode is the one that goes on the left. The more negative always goes on the left. So I draw out my aluminium half cell, solid and label everything. So solid aluminium as the electrode, aluminium 3 plus, aqueous in the solution. I'm going to draw my platinum wire going from that to the voltmeter, the high resistance voltmeter. Remember that a voltmeter being high resistance means that no current is actually allowed to flow. We're just seeing the kind of electrical push that would flow, that would happen if the voltmeter was removed. Then we're also going to draw my salt bridge and label that as potassium nitrate. And then I'm going to draw the half cell that goes on the right. This is my cathode, and this is my silver half cell. So the silver is reduced, the reduced one goes on the right, and this is the cathode. And so we have our silver solid electrode, and then our silver aqueous ions. Also, I'm going to label standard conditions, so 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cube solutions. Now, I'm going to show you two methods for how you can do this kind of question. I would definitely recommend doing it through method 1, but method 2 is quite a quick way to just double check that you've got the right answer using the first method. So, using the first method, and this is very similar to what we did in the previous video, aluminium has the most negative E cell value. That's the one that will lose the electrons, be oxidized, and therefore is the more negative one. And so we need to flip our aluminium equation around so that it's written as an oxidation, not as a reduction. So we have aluminium going to Al3 plus 3 electrons. And then likewise, because we've had that oxidation happen, we have to have reduction happen at the same time, and that happens to our silver ions. So the silver ions get reduced to silver. Now, if we want to combine our half equations, we need to make sure that our electrons cancel out on each side. We have 3 electrons in the aluminium equation, only 1 in the silver equation, and so therefore we need to times our silver equation by 3. So we have 3 lots of silver ions with 3 electrons forming 3 elemental silver. Combining those two equations, we just write down all the reactants on the reactant side, all the products on the product side, and we get that aluminium plus 3 lots of silver ions goes to Al3 plus and 3 lots of silver. Now, this is the important thing to now check back with the question. The equation that we've worked out is not the same as what we had in the question. Now, as we talked about in the last video, writing down our cell in this order, the idea that we have the negative on the left, the anode on the left, the positive, the cathode on the right, and our electron flow going from left to right, is that our calculated E cell value will always be positive. A positive E cell value is a feasible direction. So by using this method, whatever equation we end up with is the feasible equation. That is the equation that will work. Now, because this equation is different to the equation in the question you'll notice is just the reverse equation. So the equation in the question is not feasible. Essentially what that equation in the question requires is for the electrons to move from positive to negative, which we know they don't do. So we can calculate our E cell value for this half cell by doing the right minus the left for what we've written down. The right, the cathode, is our silver. The left, the anode, is our aluminium. And so we do 0.79 minus negative 0.166. And this gives us an E cell value of plus 2.45 volts. Now again, because we've worked this out in the kind of correct method of left to right, this ends up being a positive E cell value. Now, a positive E cell value, as I've mentioned before, is feasible, and negative one is non-feasible. So the actual equation in the question would have an E cell value of negative 2.45 volts. And it's kind of similar to how if we have a reversible reaction and the forwards direction is exothermic, negative value of enthalpy, the reverse direction will be endothermic, a positive value of enthalpy. So we can see the kind of links to thermodynamics here. A positive E cell value is feasible, a negative E cell value is not feasible, and if we have a reversive direction, we can just reverse the sign. So the equation in the question E cell value would be negative 2.45, and because our equation that we've worked out doesn't match the equation in the question, it's not feasible. Now the second method to do this is using something called the anti-clockwise rule. Now the really key thing for this is that when we write down our half equations, we have to write them down with the more negative at the top. So the reduction potentials must have the most negative one in terms of the E cell value at the top. Now if we have our electrochemical series given to us, as it often is, with the more negative ones at the top, more positive ones at the bottom, that's absolutely fine. But sometimes the electrochemical series is given to you with the more positive ones at the top and the more negative at the bottom. And sometimes in an exam, if they give you a number of them, they'll just randomly mix them up. And this is why I'm not so keen on this method, because it's very easy, especially in an exam situation when you're stressed, to forget this tiny little rule and therefore to get the wrong answer because you haven't got the most negative one at the top. But as long as you do have the most negative one at the top, we're going to write down our half equations, and we write these down both as reduction potentials. So we don't actually change the order of the reactions like we've done in that first method. We had to reverse our aluminium equation because it's the more negative, it will lose electrons. Here we keep them as reduction potentials. We just copy them essentially straight from the electrochemical series. So the aluminium one goes at the top, the silver one goes at the bottom, and essentially we kind of draw a circle that goes in an anti-clockwise direction, or you can draw it as 2 arrows like I've done that are moving in an anti-clockwise direction. And so this anti-clockwise direction is the feasible direction. So what we're saying here is that we have aluminium turning into Al3+, and at the same time we have silver ions, Ag+, turning into silver. And so this is the feasible direction. And so if we were to kind of make this a full expression, it would be aluminium plus 3 silver ions going to 3 silver plus an aluminium ion. Essentially what that arrow is showing you is the direction of the equation. It's telling you the aluminium equation goes in the reverse direction. But again, the full equation that we end up with is not the same as the question we have, the equation in the question, and so therefore it's not feasible. Now you can also calculate E cell values from this anti-clockwise rule. In this case, we do the bottom one minus the top one. However, I much prefer method 1, but method 2 is a really, really quick way just to double check that you've got the right answer by doing this anti-clockwise rule. The last thing to mention, as we mentioned in the previous video, is that the potentials, these electrode potentials, are intensive properties. What that means is that they're not affected by the multiplication of them. They're not affected by having multiples of them. So in the for the silver equation, to get them to balance, we've had to times it by 3 to get 3 electrons. This has made no difference to the E cell value for that half cell. The E cell value for that half cell is still plus 0.79. We've not multiplied that by 3, even though we've multiplied the actual equation by 3. So the E cell values never change in terms of the number. It's also true that the E cell values actually never change in terms of the sign. The E cell value for that particular half cell is always, for example, for the aluminium, the E cell value is always 1.66 volts. By flipping that equation round, it's still negative 1.66 volts. The only difference is the way that we write it in the actual calculation to give a positive number. So, time to have a go at an example, have a go for yourself. So, we're asked, is the equation in the question feasible? So, have a go, and the answer will be on the next slide. So, what I've not done, just for space on this slide here, is to draw out the actual picture of this, but in an exam question it's always a good idea to draw the picture out for this. So, the two half equations that we were given in the question, we have this permanganate anion going to the manganese, and we have our iodine becoming iodine. So note again that these were both written as reduction potentials, and we have our standard cell potentials here of plus 1.51 and plus 0.54 volts respectively. And again, for any of these questions, always write down oil rig and red cat and ox. So we look for the more negative E cell value. In this case, it's the iodine equation. So this is the one that's the better reducing agent. This is the one that's going to be oxidized and the one that's going to have the electrons released from it. Using the fact that it's oxidized, we can tell that that's the anode, and that the anode goes onto the negative. The anode is the left-hand side, the negative electrode. So if we're drawing a picture, iodine half cell would be the one on the left. And therefore our right-hand one would be this permanganate one. Now the permanganate one would be an example where we would need a platinum electrode, because the permanganate anion, MnO4- and the manganese ion, Mn2+, they're both aqueous species, and so we would need to use a platinum electrode. So we know that our iodine one is the more negative, it's the anode. Therefore, it's going to be releasing the electrons, so we can flip our equation the other way around. So we now have 2I- going to iodine plus 2 electrons. And then our permanganate equation stays the same, because if the iodine one has been oxidized, this permanganate one has to be reduced. Reduction is the cathode, reduction goes on the right, and so we can just keep our equation as the same direction. Then we need to combine our equations. We need our electrons to cancel. We have 2 electrons in the iodine equation, 5 in the permanganate one, and so the easiest way to get these to be equal is to times the iodine one by 5, the permanganate one by 2. This will give us 10 electrons on each side. And so then when we combine our equations, putting all of the reactants onto the reactant side, all of the products onto the product side, and cancelling out the 10 electrons on each side, we end up with an equation of 10I- plus 2 MnO4- 16H plus, going to 5 lots of iodine, 2 lots of the manganese ion, and 8 waters. And now we go back to the question, we check, does that match with the question? And yes, it does. It's exactly the same as in the question, with the exception of it's just been halved down. So in the question we had MnO4- plus HH plus. Here we have 2 MnO4- plus 16H plus. Essentially it's just twice the amount of that equation, but it's the same direction of the equation, and then therefore that is the feasible direction, that is the feasible reaction. Now sometimes questions will get you to explain why it's the feasible direction, and the best way to go about this is essentially just to say what you've done but in words. So you say that because the manganese E cell value, the half cell potential, is greater than the iodine iodide half cell potential, the manganate ion is reduced to manganese ions, while the iodide ions are oxidized to iodine. So you're just literally explaining essentially in words what you've written down already by the equations, you're just explaining in words. We can then calculate our E cell value. Remember that our E cell for this is the right minus the left. Our right is the cathode, where the reduction has taken place. The left is the anode, where the oxidation has taken place. And so our E cell value here is plus 1.51 minus plus 0.54. And this gives us an E cell value. Remember that doing it this way around always gives us a positive E cell value, and it comes out to be positive 0.97 volts. So again, remember, a positive E cell value means it's the feasible equation. And because the equation that we've written down matches the one in the question, it's a feasible reaction. Now, we could have also used the anti-clockwise rule. I'm not going to go through the full of doing this, but essentially we write down our reduction potentials. Remember to write them both down as reduction potentials, essentially take them straight from the electrochemical series, but you have to remember that the more negative one has to go on top. And so we have our iodine one on top, our manganese one on the bottom. We draw our anti-clockwise arrow, and it tells us that essentially our iodine equation goes in the reverse direction as written, and the manganese equation goes in the direction that we've written it in. If we were to combine these equations again, we would end up with exactly the same equation here, the MnO4 minus plus 8H plus 5 electrons, to get manganese 2 plus and 4H2O. That's unchanged in the way that we've written it. 2I minus, the 2 electrons in iodine. We've just flipped our iodine equation round, combine them, and it ends up being the same combination as we got above, and therefore that matches the question, and so it's feasible. And we can calculate an E cell value by doing the bottom one minus the top one, and again this also gives us an E cell of plus 0.97 volts. So thank you for watching this video. You can find lots more videos like this on my YouTube channel. If you found it helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.